All right, guys, let's learn a little bit more about energy. Hopefully last week you were able to go through the reading guide and learn a little bit. I want to talk just a little bit, summarize some things that you read about, give you some definitions, and then we're going to do a few problems related to potential and kinetic energy. So first, potential energy. Potential energy is just stored up energy. It has the potential to do work, and there's different ways that we can store energy, different kinds of potential energy we might be talking about. Gravity has the ability to cause things to move, to do work. Springs can, as you compress a spring, remember potential energy is, it's almost going to do something, but it hasn't quite done it yet, but it has the potential, and like if you smash a spring and then let go, it's going to move, right? So it has potential, and as soon as we let it go, it moves. That's spring potential energy. Chemical potential energy. Chemical energy is energy like, actually batteries are a chemical reaction that takes place in the battery, and it does cause electricity, right, so that we can run our electrical devices, but there's actually a chemical reaction in there, and before that chemical reaction takes place, there's energy. And then when that chemical reaction takes place, energy is released, and we're able to convert that into electrical energy. But that could be a place where we might see that. And then, of course, electrical energy. We all know about electrical energy and turning on lights and being able to do things with electricity. And so as we store up that electrical energy, and then that's potential energy, and then when we use it, then that becomes a different kind of energy, right? So potential energy, there's a few different things here. We're going to really focus in on gravity and look at how potential and kinetic energy are related to gravity, but then we can apply those to all these other different kinds of types of energy. Kinetic energy, so I kind of mentioned that a little bit. That's the energy of motion. When we have something, some potential energy, some energy stored up, then usually that energy makes an object do something, and as that object starts to move, we call that kinetic energy. So kinetic energy is the energy of motion. And then we have the law of conservation of energy. What this says is that energy can't be created or destroyed. It can be changed from one form to another, but the total amount of energy never changes, right? And so we're going to look at that relationship between potential energy and kinetic energy and how energy is conserved in that relationship. And so to do that, we've got a few equations that we're going to look at. So we're going to get into, like I say, focus in on potential and kinetic energy related to gravity. We're going to look at some equations, and then we're going to look at an example where we can do some calculations based on what we learned from potential and kinetic energy. Okay, so we're going to look at potential and kinetic energy related to gravity. And we have some equations that can help us look at that a little bit closer and understand it a little bit better. Now when we talk about gravity, again, gravity makes things fall, right? We've talked about gravity in this class before. We know a little bit about it. And when I hold an object, it has potential to fall, right? It's not falling yet, but as soon as I let it go, it's going to start moving, right? It has potential to do something. Gravity gives things potential energy, the potential to do something. And the amount of potential energy that object has is related to three things, and they're in this equation. The first one is its mass. So the amount of mass that the object has, or you can think of mass as like its weight. Mass is really how much stuff is in there, right? But you can think of it like weight, and so that determines how much potential energy something has, is how heavy it is. Right? The second thing that comes into play is G. G in this case stands for the acceleration due to gravity. Remember, as we previously have discussed gravity, when we drop something, it doesn't just fall at the same speed. Gravity actually makes it speed up as it falls. And it's a known amount. It speeds up by a known amount. And that known amount is 9.81 meters per second every second. So almost 10, right? Almost 10 meters per second every second. Is that fast? Well, a meter's like, what, yay big? So 1 meter, 2 meters, 3 meters, I'd be out the door somewhere, right? And I need to cover that distance in 1 second, 1 Mississippi. Whoa. Yeah, so 10 meters in 1 second, that's pretty fast. It's fast for me to run. But you know what's weird about gravity is it's not just falling at 10 meters per second, it's speeding up by that much every second. So after 1 second, it's falling about, or it's going about 10 meters per second. After 2 seconds, it's going to be going about 20 meters per second. And after 10 seconds, it's going to be going about 100 meters per second. So if you've been falling for 10 seconds, you're going about 100 meters per second. That's like a whole football field in 1 second, one Mississippi. That's pretty fast, right? So gravity increases an object's speed as it falls. It does it by a known amount, and that is the amount. That's what G stands for. H stands for the height. Depending on how high the object is, it will have more or less potential energy. If an object is really high, it has lots of potential energy. If it is low, it has less potential energy. So again, potential energy depends on those three things. Remember when we have letters next to each other, that means times. So the potential energy is equal to the mass multiplied by the acceleration due to gravity. That's always, every time 9.81. Unless you're on the moon or Jupiter or somewhere, but on Earth, it's always 9.81. And then we multiply that by how high the object is. Okay? So that's our potential energy equation. Kinetic energy, remember, is the energy of motion. And kinetic energy is related to the object's mass. M stands for mass again. And then V, in this case, is velocity. And notice the velocity here is squared. So if we're looking at mass and velocity, a change in mass is going to change my kinetic energy, but a change in its speed, its velocity, is going to also change my kinetic energy in a bigger way, right? Because I'm going to be squaring that number. So that's kind of interesting. 1/2 times the mass times the velocity squared. So if I know the mass and velocity of a certain object, I can calculate its kinetic energy. The last equation that we have written up here is that for any object, the total energy of that object is its kinetic energy plus whatever potential it still has that hasn't been turned into kinetic energy. Right? So if I take the kinetic energy and the potential energy and add those up, I get the object's total energy. So here's what we'd like to do. We're going to investigate this ball as it rolls down and up and down and up this hill. Right? And I would like to know what its potential energy is, what its kinetic energy is, and what its velocity is. I'd like to be able to find those things at any point during its travel. So here we go. We have this ball at the top of the hill. Right? It has a mass of 2 kilograms. And I'd like to start out, I'd like to know what its potential energy is. So we're going to just apply the equation here. Mass times g, acceleration due to gravity, times its height. So that's not too bad. Its mass, again, is 2. We're told 2 kilograms. G is always 9.81. So multiply by 9.81. And then times the height. In this case, the height of my heel starting out is 3. And so I'm going to take those numbers and multiply those all together. We've got 2 times 9.81 times 3, and I come out with a potential energy of 58.86. And we measure energy in joules. That's our unit for measuring energy. So 58.86 joules. Right now, it's not moving. I haven't let the ball go yet. This is all potential, right? As soon as I let it go and it starts rolling down the hill, then it's going to have some kinetic energy, some energy of motion. But right now, this is all potential. We could look at some of the other things right now. Again, it's not moving at this moment in time, so we would say that its kinetic energy would be 0 at this point. And hence, then, its velocity would also be 0. It's not moving. Right? Okay, so 58.86 joules, all this potential. I let it go, it starts rolling down the hill. And so I'm a little curious now. After I let it roll down the hill a little ways, it's maybe rolled down about 2 meters, it's got 1 meter left, right? It's 1 meter off the ground. I'd like to know at that precise moment what his potential and kinetic and his velocity is. And so we're gonna do some calculations. We're gonna use this idea of conservation of energy and these equations here and see if we can figure that out, right? So at this moment in time, it still has some height. Obviously it has some mass, and gravity is still working on it, right? Remember that gravity accelerates things, so if gravity is still working on this for a little bit longer, it's going to speed it up a little bit more, right? It still has potential to do more. It's going to be going faster when it gets to the bottom of the hill than it is now. So it still has some potential. There's still a little oomph left in there. And so I'd like to calculate what that potential energy is. And that's pretty easy to do. We're just going to apply the equation that we just did. The only thing that will be different is the height. It still weighs 2 kilograms. Gravity is still 9.81. The acceleration due to gravity is still 9.81 meters per second squared. And now, though, my height only has 1 more meter for gravity to work on it and give it a little bit more, right? And so we'll just do our multiply again. And take the calculator and 2 times 9.81 times 1. We end up with 19.62. 19.62 joules. All right, so now I'd like to find the kinetic energy, and I have an equation for kinetic energy, but here's the problem. In order for me to find the kinetic energy using this equation, I need the velocity. I need to know how fast it's going. And I don't know that. In fact, that's one of the things I'd like to find out. And so I can't just plug numbers into this equation and solve for velocity, or for kinetic energy, so because I don't have the velocity. So I'm going to have to go another route. But I do know this. I know that before this thing started, all of its energy was potential energy. And that was 58.86. So the total energy here of this ball before it started rolling was 58.86. And since energy is conserved, meaning it can be created or destroyed, just change from one form to another, what happens is some of this potential gets turned into kinetic, right? It's moving right here. So it has some kinetic energy. It still has a little potential, right? A little potential to do more, to get going faster. So it has some kinetic energy and it has some potential energy, and together that total energy needs to stay the same as it started with, 58.86. So I know that the kinetic energy plus the potential energy together have to still be 58.86 joules. Well, at this point, I know what the potential energy is, 19.62. I know what its total energy is, 58.86. And so I should be able to find out what part of that is kinetic energy by just subtracting these. Right? If this is the total energy and that portion is potential energy, if I subtract those, the leftovers are going to be kinetic energy. So that's easy to do. I'll take my calculator and I'll do 58.86 minus 19.62. I end up with 39.24. 39.24 joules. That is my kinetic energy. Again, 39.24 and 19.62 have to equal the total amount of energy, 58.86. Okay, now what I'm going to do is I'd like to know how fast this ball is going as it reaches this part of the hill. And so now I'm going to take my kinetic energy equation, and if you'll look closely, I know what the kinetic energy is. I know what a half is. I know what the mass is. Velocity is the only thing I don't know. I'm going to be solving for velocity, solving for v. This does get a little tricky because of the squared there, but nothing that we haven't done in this class before, or in our math class, excuse me. And so we should be able to do that. I'm going to walk you through and help you solve that. So let's write an equation first. To find the velocity, I'm going to need to write an equation that says the kinetic energy, 39.24, is equal to 1/2 times the mass, which is 2, times v squared, which I don't know. Well, let's do a little math here. 1/2 times 2, half of 2, 1. That's easy. So that becomes 1. remember I'm solving for v, so I got to get v by itself. That means the 1 got to go. So a number next to a letter means times. I'm going to divide by 1. You do it to one side, do it to the other. I like this one thing, it makes the math easy. Right? So 39.24 divided by 1, 39.24. That's gone here. That just stays 39.24. And I got one last step here. I'm looking for v, not v squared. So I need to get rid of the squared. Remember when we're solving, we always do the opposite, and the opposite of squaring is square root. So I'm going to take the square root, and squares and square roots cancel out and just leave v. And if I do it to one side, I got to do it to the other. Take the square root over here. Can't do that in my head, so I'm going to use my calculator. The square root of 39.24 is 6.26, rounded to the nearest hundredth. And I'm going to go with it. 6.26. This is in meters per second. So I used my kinetic energy equation, not necessarily to find the kinetic energy. I didn't have the velocity, but I used it to find the velocity, right? So that's probably the trickiest part of all these problems, finding the velocity. Now, it rolls down the hill and it's going to get to the bottom, right? So, ball is at the bottom. Is gravity going to be working on this anymore? No, I don't think so, right? It's reached the bottom. It's not going to speed up anymore. It's reached its maximum speed. There's no more potential there. There's no more potential to do anything. We know that its potential energy, in fact, is done because height. If I were to calculate its potential energy, its height would be 0. And 0 times anything is 0, right? But it just makes sense. It's not doing anything at this point. It's not speeding up. It is going. It is rolling, but it's not speeding up. So its potential energy at this point is 0. If I want to calculate its kinetic energy, well, remember, the total energy has to equal potential energy plus kinetic energy. And right now its potential is 0. Remember, its total energy, what it started out with, 58.86. So if it has 0 potential energy, all of that potential energy at the start has now been turned into kinetic energy. And kinetic energy then would be equal to 58.86 because, again, all its potential at the start has turned into now kinetic at the bottom. And we will do the same thing to solve for v. This will give us one more time to practice that solving. So let's do it. Okay? We've got kinetic energy equals 1/2 times m times v squared. This time my kinetic energy is 58.86 equals 1/2 m, which is still 2, v squared. Much the same steps as we did before. 1/2 times 2, half of 2, that's 1. I'm going to go ahead and replace that with 1. And then we're solving for v, so I need to divide by 1. 1 divided by 1, 1 v squared, it's gone. If you do it to one side, do it to the other. But 58.86 divided by 1 is 58.86. So save a little room here in my writing. We're going to erase that. We've left with v squared equals 58.86. Remember, to get rid of the squared, we take the square root because those are opposites. They cancel each other out. Just leaves v. On this side, I also have to do the square root. The square root of 58.86, 7.67. 7.67. Remember, that is in meters per second. Solve for the velocity. Gave us one more time to practice that. Same steps. 7, let's see. And green is my color for answers, right? So 7.67 meters per second. All right, so what's weird? As it comes back up the hill, we can use some of the same things again. As it goes up the hill, it's going to slow down, right? Yep, so if it's not going as fast, then that means it's lost some of its kinetic energy. But as it goes up the hill, it gains height. And now, as it comes back down the hill, it's going to have more potential to get faster again, right? And so at the top of this hill, it really looks exactly like this guy, right? Whether it's going down or coming up, its potential energy based on its mass and its height, and 9.81 that's always the same, doesn't matter if it's coming down or going up, those numbers are going to be the same. Right here, it has the same potential energy as here. Same kinetic energy as here. So its velocity at this point would be the same, right? It has slowed down from its 7.67 and is now going the same 6.26 meters per second. Now that it is at the top of the hill. And of course, as it comes down the hill, it's going to speed up again. As it hits the bottom of the hill, it's going to be the same 7.67. And then it's going to go all the way back up the hill, and it's going to get to the top, the same place where it was over here. And at the very top, it will all be turned back into potential. Same mass, same height, same 9.81, those numbers are all the same. It will again have a potential energy of 58.86, which means zero kinetic energy, which means it's not moving, and so its velocity at this point is 0 meters per second. So that's how we can investigate an object's motion and energy through the use of these equations. You have a little sheet that hopefully you've been filling out as we've been going along. That's basically your assignment today. Tomorrow I'm going to have you play around with some problems like this and investigate how fast and how much energy something has as it rolls down and up hills. But for today, take that in, soak that all in. Just remember that relationship between potential and kinetic energy, right? As an object starts up high, it has lots of potential energy, and then as it falls or rolls down, as gravity pulls it down, that potential turns into kinetic. But remember, the kinetic and the potential are always going to equal the total, right? Here, this is just a quick little example, super easy. Hopefully this makes sense a little bit. So let's say that I have a ball, and I drop the ball. It starts out with a certain amount of potential energy. Just to make the math easy, let's say that potential energy is 10. Now right here when I'm holding the ball, it has no kinetic energy, right? Its kinetic energy is 0. Now as the ball falls, it's going to gain some kinetic energy, but it's not going to be as high, so its potential to speed up is not as much as it was back here. And the cool thing is, those two are exactly related by this total energy equation. So as it drops, let's say it drops a little bit and its kinetic energy goes up to 2. What's its potential energy? Well, the kinetic energy and potential energy have to equal the total, which to start out with was 10. And so now its potential energy would be 8. And as it falls a little bit more, it's going to go faster. So it'll gain a little more kinetic energy. And let's say maybe we get down here and our kinetic energy is 5. What's its potential energy? Well, the total energy has to be 10, so its potential would be 5. And finally, as it gets to the bottom down here, and all of this potential has now turned into kinetic energy, what would its potential be? 0. We made it down to the ground, gravity can no longer act on it, and its potential energy is 0. Remember, the total energy of the system has to stay the same. Now, one last thing that we can talk about. I don't know if you've ever played around with rolling marbles or balls up hills and down hills, but some of you are probably saying when I talked about the ball being back up here at the top, you were like, that ball's not going to make it back to the top. I've rolled the ball down a hill, and it never gets back up to the same height that I let it go. And you know what? That's true. Right? This is all theoretical in a perfect world, but we have some things that cause problems. One of those problems is friction. We've talked about friction force before. We've talked about air resistance. We've talked about some resistive forces. And when this ball rolls down the hill, we have some friction. And that friction is going to slow down the ball. And when we talk about that in terms of energy, there is a certain type of energy that's given off due to friction. You probably know it, right? When you rub your hands together, they get hot. That's energy. Heat is energy. And so as the ball rolls along, we actually have little bits of energy coming off as heat. And we're losing some energy. Now it's not being destroyed. Remember, energy can't be created or destroyed, only changed from one form to another. So we would love it if all of our potential turned into kinetic energy, but it doesn't. Most of it turns into kinetic energy, but we do also lose a little bit of energy due to heat. And so because of that, we don't quite get all the way back up to the top of the hill again, back up to our 3 meters. Because the total energy, it looks like the total energy in our system isn't 58.86 anymore. But it is, again, conservation of energy is still conserved. But if we take this little 1 joule of heat that might be given off here, and this little 1 joule of heat given off from friction, and eventually maybe with all of it, we lose a couple of joules. If we take those joules of energy from heat, plus the potential energy, plus the kinetic energy, we still make it back to 58.86. Problem is, we're not dealing with a perfect world. We have some things that slow this ball down. Friction is one of those, maybe some little rocks and bumps in here, right? And when it hits those, it hits rocks and they vibrate a little bit and they roll over out of the way a little bit, and all of that takes energy to do that to those little rocks, and that's energy that's leaving the ball and going somewhere else. Again, if we gathered all the energy back together, energy is conserved. We'd have our total energy, but some of it is not in potential and kinetic energy, our equations. We lose it in other places, right? So again, when we do these equations, we're kind of talking about a perfect world. We're going to ignore friction. We're going to ignore roughness and inconsistencies in our hill or in our track. And we're going to practice using the equations. And then when you get into some higher physics or engineering courses, you can start looking at some of the other things and other places where that energy goes. And of course, those equations are going to get a little more complicated. But energy, I love it. Potential and kinetic energy, fun stuff for sure. Fill out this paper, and then we'll have you do some problems tomorrow.